Hi, Assalamualaikum and salam sejahtera. My name is NOOR SHAHIRAH binti YUSERI. My matrix number is THT20058. Okay, I'm from group 5, which is my group members is EZDHAM and THIVIYA Patrick SAMY. Okay, I will represent to you chapter 7, which is gases. Okay, this chapter will discuss about the general properties of gas. Okay, in general properties of gas, we have four types. Which is for the first one is gas can be compressed. Second, gas assume the volume and shape of their containers, and third, low densities, and for the last one is particles of gas are far apart and fill the available space. As we can see, gas are all around us, which is atmosphere of the earth, bubbles in soda, fumes from volcanoes, and the last one is heliums in balloons. So we go for the next slide. Okay, in the gases, we has the gas laws. In gas laws has three law, which is Boyle's law, Charles law, and Avogadro's law. Okay, the definition of Boyle's law is the volume of its amount of gas at constant temperature is inversely proportional to the gas pressure. Okay, the Charles law is the volume of a fixed amount of gas at constant pressure is directly proportional to the absolute temperature of the gas in Kelvin. Okay, for the last one, for the last law is Avogadro's law. At constant pressure and temperature, the volume of a gas is directly proportional to the number of moles of the gas present. So for the formula is the Boyle's law. Okay, for the formula Boyle's law is P1 V1 equal to P2 V2. Okay, V stand for volume and P stand for pressure. Okay, when the volume is high, the pressure is low. We can see the graph will show you. Okay, for the second is the Charles law. V1 divided by T1 equal V2 divided by T2. Okay, the Charles law, we must convert the temperature to Kelvin. Okay, how to get the value in Kelvin? So the formula is temperature Celsius must at 273.15 and we can get the value in the Kelvin. Okay, for example, we can see that two situation, which is a balloon inside the room and second balloon outside in the snow. Okay, balloon inside the room is volume is high and the temperature also high. The second balloon outside in the snow, the volume is low and the temperature will become low. Okay, so we go for the third formula, which is Avogadro's law. Okay, V1 divided by N1 equal by V2 divided by N2. Okay, V is a volume of gas and N is the number of moles of the gas. So we can convert the formula. So the combination of the law is P1 V1 divided by T1 equal P2 V2 divided by T2. So we know the temperature. So we know that the pressure is. So we can know that P is a pressure, V is a volume, T is a temperature. Okay. So we go for the next slide. Ideal gas equation. Okay, what is an ideal gas equation? Okay, This is a combination of Boyle's law, Carnot's law, and Avogadro's law. The formula is PV equal nRT. Okay, in unit pressure ideal gas equation, we have two, which is ATM and Nm power of -2 Pa. So we go for the first unit, which is ATM. The unit of volume is L or dm power of 3. Volume of R is 0.082 to 06. And for the last one is unit of R is LATM divided by mole K. Okay, for the next unit is Nm power of -2 Pa. Unit of a volume is m power of 3. Volume of R is 8.314. Unit of R is Nm divided by mole K equal J. Okay, for the molar mass and a density calculation, calculate by rearranging the ideal gas equation. The density of gas is the formula density of gas is density equal m divided by v. Okay, Dalton's law of partial pressure is the total pressure exerted by mixture of the gases is equal to the sum of partial pressure, which is PT equal PA plus PB plus PC and so on. So the formula, the last one is P total equal to N total RT divided by V. I think that's all from my chapter 7. So we go for the next chapter, which is chapter 8.
Assalamualaikum, my name is Awang EZZAUDDIN and my student number is TG20068, and I will cover the chapter 8 of chemistry, which is thermochemistry. Thermochemistry is divided by two, which is exothermic reaction and endothermic reaction. Endothermic reaction where the delta H is positive, meaning that the heat is absorbed by the surrounding, for example where the ice is melting. And for exothermic reaction where the delta H is negative, which means that the heat is released from the system surrounding, for example combustion. Over here is the graph for endothermic reaction where the heat is being observed and then released. And for the exothermic where the energy is being observed and then be released again. Next is the enthalpy. Enthalpy change where the heat is observed during the reaction constant pressure, and enthalpy reaction is the change where the chemical reaction is associated. The standard enthalpy, meaning that the change of a particular reaction that occur at 25 degrees Celsius and 1 atm. There are two types of enthalpy. First is enthalpy formation, or delta HF. The heat where the heat change 1 mole of its compound, where it's form its element in their most stable state. Second is the enthalpy combustion, where delta HC, where the heat is released when one mole release a heat substance in its burning in excess oxygen. And now is the calorimetry. Where here is the image of calorimetry, and over here is the bomb calorimeter. Constant pressure for the simple calorimeter, where the heat of the outer styrofoam, over here the cup, is insulated the reaction mixture from the surrounding, and from that we know that the heat is released by the reaction is absorbed by the solution and the calorimeter. And here is the important term in the calorimeter. Specific heat capacity is the amount of heat required to raise the temperature of 1 gram of this substance by the degree Celsius. And heat capacity is the amount of heat required to raise the temperature of the given quantity for the substance by 1 degree Celsius. And now we will talk about Hess law. This Hess law is the state when the reactant are converted to a product. The change in the enthalpy is the same whether the reaction takes place in one step or in the series of steps. The enthalpy change depends on the initial and final state of the reactant and product, but it's independent for the path taken. That's all. Thank you.
Hi, my name is Divya Patrick SAMY. My student ID number is TG20029. Now I'm going to present the chapter 9, which is reaction kinetics. There are three subtopics in this chapter. The first subtopic is reaction rate. Reaction rate: change in the concentration of a reactant or a product with time. The unit of the rate of reaction is ms-1. The second is differential rate equation. A differential rate equation relates the rate of disappearance of reactants and the rate of appearance, which is formation of the products. And the third is rate law, which is rate equation. Express, expresses the relationship of rate of a reaction to the rate constant and the concentration of the reactants. Order of reaction is always defined in terms of reactant, which is not the product's, concentrations. The order of a reactant is now related to the stoichiometric coefficients of the reactants in the band's chemical equation. The next is going to explain about the half-life. What is a half-life? Half-life is the time required for the concentration of a reactant to decreases to half of its initial value. Next is the order reaction. Here got three types of order reaction, which are zero order reaction, first order reaction, and also the second order reaction. So each of the order reaction consists of rate law, unit of rate constant, integrated rate law, and also half-life. For the zero order reaction, rate law is a zero order reaction is a reaction which independent to the concentration of the reactant. The unit of the rate constant for zero order reaction is ms-1. So the for the first order reaction, the rate law for the first order reaction. A first order reaction is a reaction whereby its rate depends on the concentration of reactant raised to the first power. The unit rate for the first order reaction is S-1. Next is the second order reaction. Rate law of second order reaction. A second order reaction is a reaction which the rate depends on the concentration of one reactant raised to the second power or on the concentration of two different reactants each raised to the first power. So the unit of the rate constant for the second order reaction is m negative one S negative one. Next, the second subtopic. The second subtopic is collision theory and transition state theory. Now I am going to explain about the collision theory. Collision theory is the theory to explain the rate of chemical reactance. It is based on the equation which is rate is equals to number of effective collision divided by time. The collision theory is based on the ideas which are molecule must collide to react. The second is collision involved is an effective collision. So the molecule must possess a certain minimal kinetic energy, which is activation energy, to initiate the chemical reaction. Also, the molecule must collide in the right orientation in order for the reaction to occur. So there are two requirements of effective collision. The first is minimum energy. For the minimum energy, activation energy is the minimum amount of energy required to initiate a chemical reaction. Molecule must possess a minimum energy for a chemical reaction to occur. Activation energy is the barrier that prevents less energetic molecules from reacting. The second requirement is correct orientation. So next is the transition state theory. The transition state, the configuration of the atom of the colliding species of the time of the collisions. The activated complex, the species formed at the transition state. The next is energy profile diagram. What is energy profile diagram? A reaction profile shows a potential energy plotted as a function of the progress of the reaction. The difference in potential energies between the products and the reactant is delta H for the reaction. Reactant molecule must have enough energy to overcome an energy barrier separating products from the reactants. So there are two types of reaction, which is exothermic reaction and also endothermic reaction. So this graph shows the exothermic reaction, and the graph on the right shows the example of the exothermic reaction. The second is the endothermic reaction. Here the graph shows the endothermic reaction, and also the graph on the right side is the example of the endothermic reaction. Okay. The last subtopic is factors affecting reaction rate. So there are five types of factors that are affecting the reaction rate. The first is concentration of reactants. A concentration of reactants is increases, the frequency of collision also increases. So the collision is directly proportional to the concentration. This would also result in the increases in the quantity of effective collision. Thus the reaction rate increases. So the reaction rate is directly proportional to the concentration of the reactant. It is depending on its rate order. The second factor is pressure. When the pressure is applied, the volume decreases, the number of molecules per unit volume increases, resulting in more collisions per second. number of effective correction increases, therefore the rate of reaction also increases. So the third is temperature. As the temperature increases, kinetic energy of molecules also increases. So more the collision occur in a given time. Furthermore, the higher the kinetic energy, the higher the energy of the effective collisions. So more molecule will have energy greater than activation energy. Thus the rate of reaction increases. As, as a conclusion, the kinetic energy of molecule is directly proportional to the temperature. The higher the temperature, the higher the kinetic energy, thus the higher the rate of the reaction. So next is particle size. The smaller the size of reacting particles, the greater the total surface area exposed for reaction, thus the faster the reaction. The greater surface area causes a greater frequency of collision, thus the increasing the reaction rate. And for last is catalyst. A catalyst is a substance that provides an alternative pathway by lowering the activation energy to increases the rate of a chemical reaction without itself being consumed. A catalyst also increases the rate by increasing the frequency of effective collision, that is, by decreasing the activation energy with the correct orientation. Catalysts will not affect the enthalpy of reactant or the product. So, without the catalyst, the reaction occurs will be slow, but with the presence of the catalyst, for example, manganese oxide, which is the one type of the catalyst, so it will it will faster the reactions.